So the main topics will be more or less high or low level methods to handle GPUs in Julia. Can be arrays and what are kernels and how do you use them to offload our computations to GPUs. So do it for GPU programming, and there are packages that target GPUs from the current vendors. So we have CUDA for NVIDIA GPUs, AMD GPUs for ROCm, where ROCm is the stack for GPU programming. One API is a software stack that Intel is building that in theory should be able to handle GPUs from all vendors. And so I was saying, yes, the last package, Metal, for that is the graphical toolkit that Apple built for its newer Apple Silicon machines. So as it is today, CUDA is the most mature, also in terms of tooling that is built around it. AMD GPU is kind of behind, but still usable in production. They're making great strides in that sense. One API and Metal are fun part, but especially integration with vendor libraries that we'll go through in a moment might be a bit lacking. And there's probably still a lot of low-hanging fruits to improve performance, but they're usable, especially when for integrated Intel GPUs, they're functional. So especially in the data center space, NVIDIA is the big player, of course. But C has made a lot of progress in that sense. And so far, 3 of the machines in the top 10 of the top 500, there is this list of the 500 most powerful supercomputers, and them. So the very first, fastest supercomputer in the world is eBase, and also the second. Lumi is number 8, I think, in the November list, and is indeed. So we will show some code examples that target all 4 frameworks, but some things only exist on the CUDA version. Often that we will have a list CUDA who might be lacking at the moment. With all frameworks, you get both, kind of high-level abstractions that let you use GPUs as if they were normal CPU arrays. So there is not a lot of specific knowledge that is needed. But at the same time, also offer primitives for lower level approach. So we can have a lot more deeper control. If you're looking for more even high level type of control, there is the kernel package that can be used to write code that is agnostic to the vendor and can run on GPUs from all vendors and also fall back onto CPU if none of them are available. So to set up, install the right package. So Lumi that I will use throughout this demo is based on name. So I already installed AMD GPU. And from the Julia side, on top of that, it is needed and toolkits that are installed. Now, normally, if you're using an HPC system, those are already available. So, for example, for us, Lumi will not be a big problem. If you're using your machine, then you will need to install them yourself. A list for AMD and Intel. If you use CUDA.jl, it will take care of installing the CUDA toolkit for you. With AMD, software for is a useful link here that will explain how to do it. If you're using Linux, it's on most distributions. And because AMD only releases packages, I think, for either OpenSUSE or Debian-derived systems, but all major distributions repackage them. And with Intel, since we're on Lumi, the AMD driver and toolkit are already installed, so we don't need to bother so much with it. Yes, we will need to have access to a GPU device to follow this. So this is mainly meant for people who maybe take this training outside of a workshop. In this case, we have already access to an HPC system, so that's not a problem. Other ways to get access to a CPU are, of course, to a GPU is, of course, if you have one on your machine, then it's just a matter of installing drivers and toolkits. There is a commercial cloud called Julia Hub, where you can get, already function installation of Julia and GPU hardware, and it sits in the cloud, so you pay per use. And you can also use Google Colab. That requires a Google account, and you have to install Julia yourselves. There is a nice tutorial on how you can use a Colab notebook for Julia applications, since it's not natively supported. But you get some NVIDIA GPUs for free, so it can be worth the effort. So before delving, into the code, I guess one important aspect to talk about is how GPUs and CPUs differ. So this can help us to understand why GPUs need to be treated differently compared to CPUs when we develop our algorithms and when we implement them. So in this picture, we can see a CPU die and a GPU die. And the first striking difference that comes to mind is that if you look at, percentage of area of this surface, the ALU, that stands for arithmetical or logical unit, that is the number crunching part, so the one that contains our floating point operations and so on, is dominating in the GPU part, whereas it is only a part in the CPU. So CPU cores have a much larger infrastructure for control of the execution, and instructions for heuristics to choose the order at which operations are performed, and more flow control, whereas GPU is all about crunching numbers. And this is because GPUs, as the name says, graphical processing units, were originally developed for graphics rendering applications, where if you have to render several frames in an animation, you can treat each pixel more or less independently. So you have many arithmetical parts of the circuit, or many arithmetic circuits, and execution control is not that important. So GPU threads in general tend to be much more lightweight compared to CPUs, and context switching is much faster. So both have their own separated memory, DRAM here. So in order to be able to transfer data to and from GPUs, you need to route this data through a PCI Express link in most cases. And this tends to be one of the major bottlenecks of when you use GPUs, because this link is slower compared to memory sitting very close to the computation units. So one requirement, or one good thing when we use GPUs, is that we have to make sure that whatever computation we want to run on it is large enough that it compensates for this delay or this latency due to the transfer of the data through the PCI Express link. Then, apart from that, each one of the green squares here is a core, and each core has some local register where its own data sits. And cores on a GPUs are usually grouped into what in NVIDIA language are called streaming multiprocessors. AMD calls them compute units. There is a lot of difference in naming between the vendors to indicate the same thing. So we'll try to keep more or less both in the loop. So each one of the gray squares is a group of GPU cores with one control unit and one local memory. This is an L1 cache, and cores on the streaming multiprocessor can access this memory, even though it's slightly slower than the local registers, of course. Even within a GPU, reading from the video memory, this DRAM here, can be a bit more expensive operation. So a lot of times optimizing a GPU algorithm is about making some clever reading from memory so that we minimize the number of times that each core has to read data from somewhere else. But this kind of gives us a good idea. So when we're on GPUs, we want to, read to and from memory as little as possible and keep the data residing in this block as much as we can, because copying it back and forth is the really expensive operation here. Yes, so this is just a summary of what I just talked about. And the fact that we have so many compute elements can enable extreme scaling for data parallel tasks. So oftentimes, most of the cores will be doing the same operation on different chunks of an array. So this is what is called data parallelism. In this case, single program, multiple data, SPMD. It's kind of like single instruction, multiple data. Have their own memory, so things need to be copied back and forth. And yeah, GPU cores are grouped into streaming multiprocessors or compute units, depending on the vendor. So generally speaking, we can use GPUs just by using a different type of array. So in Julia. So we have the base array type that is our normal array that sits on the CPU memory or on the RAM, of the host. And then the GPU packages define their own types of array. So CUDA defines a Q array, and AMD GPU defines ROC array, where ROCm is the name of the software stack the AMD has built. One array for one API and MTL array for Metal. And these types are descend from the abstract array type. So they basically tend to be served by the same methods or functions. So very often we can perform more or less the same operations on a base array and on a ROC array or on a Q array. So we can take an example now. I've already logged in on a GPU node on Lumi, as you can see, and you can see that I've used the command that you can find in the setup section of this lesson material. So srun and one with a small g partition and so on. You can look it up in the setup section, or actually I can show you. Maybe it's better. You have this command here that you can just copy paste on the login node in Lumi and just change the time if you want to keep running in the REPL for a while. And this will give you a shell on a GPU node on Lumi. So we were here. So I will start, or I will load the modules first. And then Julia, and Julia, AMD GPU. Like we were saying yesterday, Julia AMD GPU does not contain a whole Julia installation, much like Julia MPI. It's just a module that is used to set some environment variables and load in the graphical toolkit so we can use GPUs. But the binary is only part of the Julia module. Let us run this. And then we can load the AMD GPU module. There will be most likely some pre-compiling involved, but it will get there. Okay, so what we're doing in this example is just creating, normal array and then calling the rock array constructor around it. So what this will do is just build a GPU array around a vector that we just created. So it's a 1, 2, 3. It's lagging a lot. For and now the REPL will tell me that I have a rock array. So this basically tells me that this memory is sitting on the GPU. And throughout these examples, we will use G for everything that sits on the GPU. And that's because the first, implementations of GPU programming were done by NVIDIA, and in their language, D stands for device and is the GPU or the accelerator, and H is the host and instead is the CPU. So you will hear a lot about moving data from host to device and from device to host. That basically means from CPU to GPU. So now we have this AD, and we can, for example, increment by 1 each one of the values that we have in this array. And we will have all of them increased by 1. And this is all happening directly on the GPU. So for us as users, this is very transparent. We're not really doing anything different from normal, array programming in Julia. And then if we want to move it back to the CPU, we just call the array constructor on it. And now we have a 4-element vector. So as you could see, this operation was much quicker. And the bottleneck a lot of times is really the override of copying data back and forth. So we can do something more realistic, that is matrix multiplication. We create 2 arrays full of random, one on the CPU and one on the GPU, and then compare the performance. So we use benchmark tools for, as usual, to time operation. That I hadn't installed, so we'll have to install it now. In the meantime, we can just give a look at this code. So we're using btime to do normal matrix multiplication. So let's just create the right arrays. This will be a 2 million by 2 billion by 2 billion array. And then we have the same array on the device. So we can do some matrix multiplication. The dollar, as you may remember, is used to escape a variable into the btime macro. And this will benchmark this function for us. When we try to do the same thing on a device array, we need to do something, which is that calls onto a GPU computation are asynchronous. That means that when I execute this function, so the same matrix multiplication on a GPU array, the Julia runtime will take care of dispatching this function on the GPU, and then it will just return. Like, it will tell the GPU execute this, and then go back to whatever it is doing. So in order to time this properly, we have to do this synchronize call. That basically says, okay, let's wait for the GPU to finish whatever it is doing, so we know that we can collect that data back. So that's why we need to embed the btime call into this begin end block, because we need to be able to synchronize. There is also a macro in AMD GPUs that we can just call around this. I think it just called AMD GPU.sync, but we can try to run it like this for now. Begin. So we do the same multiplication with the array, GPU array. And then we basically tell the GPU or the runtime to wait for it, and then we end. And this will run basically the same benchmark. So this is something to keep in mind when GPUs are used. The calls are asynchronous, if you're familiar with this term. That means that they're basically launched, but the runtime is not waiting for them to finish. And if we want to, do an operation like timing this, we need to wait for it to synchronize. So as you can see, there was a huge speed up from 6 milliseconds to 78 microseconds. This allocation is a bit, doesn't really count on what we're allocating on the GPUs. The size of the array will have an effect, because as I've been telling you, the real bottleneck is moving the data back and forth. So the more data we have on the GPU, the more busy we keep it while it sits on the GPU, the better it is for us in terms of performance. But you can test this yourself. You don't have to believe me. But this will be a recurring theme, minimizing exchange of memory and make sure that memory is as local as possible when we run operations in the GPU. Vendor libraries. This is an interesting topic. So originally NVIDIA, but also AMD and Intel nowadays have developed libraries that contain precompiled operations that are commonly performed. For example, the basic BLAS package, that is that library that contains, matrix multiplications and decompositions like QR and a lot of like linear algebra primitives. They have been implemented by CUDA and ROCm developers with faster code paths, and this can be used to accelerate such computations when they happen on the GPU. Same thing is for fast Fourier transforms, linear solvers for linear algebra systems, primitives that are used, for example, in neural networks that NVIDIA calls QGNN and AMD calls MIOpen. On NVIDIA and AMD, they mostly just work without any real effort. On Intel, there is a port of the famous Intel MKL, mathematical kernel library, to also work on one API, and it's not really tested yet, but if you use the oneAPI.jl package, there are some things available already there. Not all of the primitives are ported, as far as I know. And these kernels are wrapped in their vendor library, and you just use the relevant GPU array. So just to give an example, let's create, or we can actually reuse the same array that we had before. So let's make an array of random numbers. So the mdgp.rand will just create the array directly on the GPU. And we can do, for example, regular matrix multiplication. And that is quite interesting because it will directly be dispatched. We don't see it as users, but it will be directly dispatched to ROC BLAS, that is the AMD implementation of the BLAS subroutines. So we can take advantage of this, accelerated operations without really having to do much. Same thing, for example, we can do QR factorization. We can use the ROC solver library that is shipped with AMD GPU. I would just go ROC solver.qr, and we get the QR decomposition of this matrix as device or as programmed by AMD. Same thing for an FFT. Go ROC fft.fft array. And oops. First we have to plan the FFT. Yes, the FFT part is a bit more, it requires one more operation, that is planning the FFT. So it will, I think it was called like this. No, just like this. Where are ROC array? I had just tried this earlier today. I will have to look at the documentation again, but sorry, I thought I tried this. Yes, but we can basically use accelerated vendor libraries to perform these operations faster. ROC array T.
At least for me, the ROC FFT just worked. Did you do something else?
It could be that maybe I did the QR decomposition of it, and you can't do it on that type. Because I did a QR factorization first. No, A doesn't exist. It was called AD. That was my problem.
Okay.
FFT of AD. Yeah. Because A was sitting on the CPU still. Yeah, and now I just computed FFT of this. Sorry. I was reading at the code on the left and forgot that I changed the name. Yes. So from the perspective of the user, this basically means that we have access to these optimized primitives from the vendor directly, and they're exposed under the respective packages. And what is cool is that they implement the same interfaces as defined, for example, by the abstract FFT in Julia or by the linear algebra package in Julia. So we can use them in more or less the same way. We just refer them from under their package. But they should work pretty much in the same way, just faster because they've been implemented by the vendor. This exercise you can try yourself, because we've done maybe a bit mixing them up, two things. One is to create a random array on the CPU and then converting it to a ROC array or Q array. And in another instance, we've used the run function already from the GPU library. And this can lead to a difference, or leads to a difference. That is that a normal CPU array is normally a double precision number, so float 32 in Julia language, sort of. Whereas the rand called directly on the GPU will give us a single precision, so float 32. Sorry, this is float 64, yes, and this is float 32. And that's because GPUs tend to perform better with float 32s compared to double precision numbers. So if we want to enforce double precision for some reason, this is the route that we have to go. So doing a CPU array and then copying it rather than instantiating it already on the GPU. And depending on your application, this can have an effect. Moving on, and I guess we can take this just before the break. GPU arrays are basically just arrays from a programmatic perspective, which means that we can use many of Julia's abstractions. So for example, we did element-wise addition in a completely transparent way. But generally speaking, we can use any of the, higher order Julia constructs like broadcast, map, reduce, accumulate, all sorts of things. So for example, we can do like before a map, let's create, for example, an array of ones. And then we can, for example, do kind of the same thing. So increase them all of 1. So the map construct, as if you don't remember, basically performs whatever is in the do and block on each element of a collection. So we'll have x plus 1. And this will return vector of 2. Oh, this should have been, sorry. And now we can do the same thing. And we get a 5-element ROC array. We can do a reduction. So take, for example, summing all of the elements of the array. Oops. And this will perform a reduction operation. We can accumulate over one axis. In this case, it's a vector, so we only have one axis that we can accumulate on. Yes, so GPU array programming, for the most part, is really not different from any of the array operations that we have seen so far for normal CPU arrays in Julia. And this is kind of the beauty of this. So it's really transparent for the user to use GPUs or CPU arrays. And on top of that, we get optimized, primitive operations through these vendor libraries. So this is all quite powerful, but a lot of times it's not enough. In some cases, we need to write our own algorithms that perform operations on arrays. And in these cases, we have to write what is called a GPU kernel. A kernel in this context is basically a function or a series of operations that is taken and dispatched onto the GPU, where it runs, and then the results are returned to the CPU. So in some cases, we have to develop our own algorithms, especially if we want to optimize some things. And this will be the topic of the next section of this episode. But maybe we could take a break now.
Yes.
So where we stopped is at the point where, sometimes the primitives that the vendor provides us might not be enough. So we have to write our own kernels or functions that can run on the GPU. We can take an example of this, where we just want to add two vectors. So we have this vadd function that basically loops through vectors A and B, or in this case just A, and then adds the corresponding elements of A and B into C. So I can just put this inside the REPL, have this vadd function, and then I can test it with these arrays. So I have an array of 5s, an array of 1s, and then I set them. And in C, I will have 6s. So all cool for now. In principle, you shouldn't do this. But in principle, we can run this directly on the GPU. So we can have, for example, the corresponding GPU arrays. So AD is copied from A, BD from B, and C is also filled with 1s. And then we can try to run this as it is. And this will actually run, but it will be a bit horrible, because what this code is actually doing is dispatching this on the GPU. So this rock macro basically takes whatever function we pass to it and dispatches it on the GPU. For CUDA, it would be the same, but the macro would be called CU or CUDA, so on for the other vendors. But what this code is doing is basically having every GPU core, GPU thread performing this loop by itself. So what is happening is that basically ROCm doesn't know how to spread this work onto several cores. So in order to make this work properly, we have to instruct the runtime on how to, spread this work over several cores. And this is where the concept of where the concept of threads and blocks comes in. So you can think of them as you have a variable that is the thread ID. That is basically the thread ID from multithreading, if you remember that. So it basically indicates the local number of the whatever thread is being executed in a GPU right now. And then you have the size of a block. A block is a group of threads, basically. So it would be the n threads that you get from multithreading. So basically, you have a block of threads that work together, and each block has to reside on one streaming multiprocessor or compute unit if you're speaking AMD. And what we have to do is basically tell the runtime that each index of the array has to be mapped of the thread index in a block. So one first step towards that is to swap the I that we gave to the loop with the index, with a thread ID. And for NVIDIA, there is a special function called thread idx.x, and for AMD is called work item index.x. So let's redefine this vadd function using these primitives. So we're saying that in this case, the index is just the index of the work item. Work item is AMD speak for thread ID. And we can create, again, an array of ones and an array of, two arrays of ones, 1 multiplied by 2 and 1 multiplied by 3. So we have 5 again, and then C will be similar to A. So in this case, the total number of elements is the length of A. So it would be 512 because we have square root of 2 to the 9th. And we dispatch again this kernel using the rock macro. And then we tell it what the group size is. The group size is the size of a block in NVIDIA language. So it's very easy to mix up words here. So groups of threads are called blocks in NVIDIA, or groups in AMD, even though now the nomenclature is kind of more falling together. And each thread can be identified by a thread ID that is called thread IDX for NVIDIA and work item IDX for AMD, which is what we're using now. So when we dispatch this kernel, we pass it the group size, and then we do this addition. And this will have executed, and then we can check that if we bring this back to the CPU, this is equal to 5, because we're summing 2s and 3s, and it's true. So all good, except for one small hiccup. That is that a group or a block of threads has to be sitting on the same streaming multiprocessor. So if we go back to this picture, it means that each one of these blocks has to be in one of the gray squares. But what happens if we have an array that contains more blocks, or that contains more elements that can be fit on a single streaming multiprocessor? Then we have to create several blocks, several work groups that can, span different streaming multiprocessors. The size of what can be fit in one streaming multiprocessor can be found programmatically. So, for example, we can check here that passes 0 because we only have one device, and this tells us here maximum threads per block is 124. So it is basically saying that we can't have arrays that are larger than 1024. Otherwise, they will not be able to fit all in one streaming multiprocessor. So if we want to take advantage of the fact that a GPU has more than one streaming multiprocessor, then we have to spawn several blocks. And we do something quite similar. So we have the dimension of a block and the index of a block. So we'll just first copy paste this code, and then we can check what it actually means. So let's redefine the vadd function. So what we're saying is that the index that of the number that we want to sum is equal to the work item, so the thread ID, plus the number of the work group, so the number of the block that we're in, times the size of a single work group. So imagine that, for example, if we go back to this figure, that I think it makes things easier. We want to refer to this number that would be the 6th or the 7th actually position of this array, and each block has a size of 4. Then this number can be identified as 3, so the index within its own block, plus how many blocks we have before, so the block index times the size of a single block. So we have one block before of size 4, so it would be 1 times 4 plus the 3 that we have here. This gets us to the 7, since in this case we're starting to count from 0. So this is the most general code that we can write that can loop through an array and that can take advantage of as many semi-multiprocessors as it can. So you will see this type of syntax a lot. So thread ID or work item .x plus the number of the work item times of the work group times the dimension of a work group. You may wonder why we have all this .x's. That is because the index of a thread or a work group can be multidimensional. So in this case, we have only a linear array, like a 1D vector, but this could be in 2 dimensions or 3 dimensions. So for example, if I want to, some data structures are better represented in 2-dimensional, 3-dimensional array. Let's say that you have, for example, something that is defined over a 2D mesh, like a square divided in cells, then it's much easier to address the position of a number in a matrix by using 2-dimensional arrays compared to 1. In this case, we only take advantage of the X dimension. Then what we have to check for is that since we're dividing our threads in blocks, it's not always that the length of the array that we want to loop through is an exact multiple of the size of one block. So we will most likely spawn one block that is not completely full. So we have to check that I is within the boundaries of the array. So if it is, we do the sum that we wanted to do before. We can do the same thing that we were doing before. So I have a GPU array of 2s and one made of 3s. And C is similar to A. Then what we do in this case is that we're telling the runtime that we want to run with a group size of 256. That is usually a sensible choice when we're running GPU computations. And then the grid size, that is basically the number of blocks that we want to spawn, is the small integer, the smallest integer that is larger than the length divided by the group size. So what I'm saying with this is basically I have 512 elements in one direction. My group size is 256. How many blocks do I need? And grid size in this case will be equal to 2. So I will have 1 plus a bit that is full. And then I can run this more or less in the same way that I was doing before. So the group size, as before, is equal to the group size. We pass it also the grid size, so the number of blocks that we want to spawn. And then we can do v-add CAB. And this will have run more or less in the same way as it did before. So we can check that it actually worked. And it did. So yes, there are a lot of names here, but the idea is that we have a number of threads that are grouped in blocks, and we need to define a number of blocks so that we can take advantage of several semi-multiprocessor. All of this said with NVIDIA words. On AMD, you just exchange thread for work item and work group for block, but it means exactly the same thing. And we've been prescribing 256. That is what is recommended most of the times. And that's because the more threads we use, usually the better the performance, because we're keeping the GPU the busiest. But this might not be always optimal. So to optimize the number of threads that we need, that depends also on the kernel that we're running. We can first create a kernel without actually launching it. And then there is an API that lets us compute programmatically what is an optimal number of threads that we can run. And this used to be much easier with the CUDA API, but now it works quite well also with AMD. If you look it up for NVIDIA, there are also some like online calculators of occupancy. But how we do it in this case is something like this. So we say that a kernel is the function that we want to launch, but we do kind of like a dry run. So we don't actually launch it. And we do CAB. And this will return like a pointer to the kernel that I want to launch. And then I can compute the occupancy as given by the runtime to me. So I can look at its launch configuration of the kernel. And it will tell me that the optimal grid size will be 220, and the optimal group size is 1024. So this is actually telling me that the size of a block should be 1024, and the grid size, so the number of blocks, is this number. And then I can launch it in the way that the runtime as computed it would be the most optimal way of doing it. This tends to be a point of where a lot of optimization can be done. So determining the right group size and the right number of threads to keep the GPU the busiest. And with this, occupancy API, it becomes quite easy to do it. And the reason why we need an API to do it is because it depends on both the type of problem that we want to solve and also on the hardware, because different GPUs are different, for example, size of streaming multiprocessor, different number of threads that each streaming multiprocessor can juggle with. So we can't really pre-compute this without knowing the type of problem and also the type of hardware that we're dealing with. And this is kind of like middle level type of approach that we could take, where we actually keep control of the number of threads that are spawned and how they're spread throughout the GPU. We can also use a package called kernel abstractions that is used to write kernels that don't depend on the GPU vendor that we're dealing with. Any case can also run on the CPU. I will first copy this function. I think this will need to be installed actually. Yep. But we can give a look at the code in the meantime. So to use kernel abstractions, we use this @kernel macro that says that this function can be offloaded to a GPU. And what is cool, in my opinion, about this is that we can kind of abstract away the differences between the different vendors, because we can just use this index macro that basically will convert into, work item.idx or threadid.idx or whatever the vendor wants us to have there. And it will also take care of doing that addition that we did earlier, that to take into account the work group size and the work group index. So this basically gives us directly the index that we want to go for during the computation. And we can just compile this function here. And this const macro is just to say that the vectors A and B will not be overwritten. They will just be read, and this allows for some optimization at read time. And it corresponds to the restrict keyword in CUDA, if you're more familiar with it. But it's basically a way of us telling the compiler, look, this two will not be changed, so it can lead to some improvement in performance. So we did this kernel function VAdd, and then what I did was just to build a wrapper around it, where it will get the backend of the vectors that we want to sum. So this A can be a CPU array, and then this function will be specialized on a CPU. If this A is a rock array, then it will build a ROCm kernel. If it's a metal array, same thing. So this is just a way for us to understand what array we're dealing with and then launch a specific kernel with it. And then we just launch it. And we just pass it the total number of elements that we want to work with, that is the size of C. So this is just a way of having a thin wrapper on top of the function that we want to build that will just launch with whatever data. And I think this is quite interesting because it allows us to do something like this. We can just generate a number of CPU arrays and called my VAdd on it. And this will be a bit, sorry. Let me exit this session. Because I think I overwritten some variables that I shouldn't have. Okay, let me get my functions again. Yes, now it should work. And then I will grab my CPU vectors. And C now will contain 5s as we were expecting. And then I can just turn these arrays into GPU arrays. And I call the same function just, passing the GPU arrays. And this will take, again, a bit longer, just the first time to compile it. And of course, copy the things back and forth, since it's only a 10-element vector. And I get the same 5s also on the GPU. So I basically wrote one function, and I wrapped with a just very thin wrap around it. And I can run exactly the same code both on the CPU and the GPU. And the indexing is taken care of. There are also some further optimizations that can be done to use the local memory of each thread on the GPU. This is a bit outside of the scope of this particular workshop, but it can be interesting. But this makes things quite portable. And also on top of that, the kernel abstractions.jl actually takes care of doing that little trick that we did earlier to use the occupancy API to determine the optimal number of threads and grid size. It will do it behind the curtains for us, and the optimal number of threads is determined automatically. There are some limitations to use kernel abstractions. It can't be used for everything, but a lot of times it lets us, write the same code and run it pretty much everywhere. So at least for initial prototyping, this can be a very good way of writing backend agnostic code. So yes, it works quite simply. We use this kernel macro, and then we call it depending on the type of data that we pass to it. Just a couple of points that should be made clear. When we write kernels, we can use most of Julia language features, but not stuff that requires the runtime library, which means that you cannot call dynamic functions and you cannot allocate memory within functions. That's because this code is compiled before it's then dispatched to the GPU. So anything that cannot be known at compile time will give you problems when you try to run it on the GPU. And a lot of times you will get some errors saying things like GPU code could not be compiled due to dynamic something. So it will be a message that will try to point in that direction. And I'm going back to what I was telling you before. When we access the threads and blocks ourselves, we tend to put these X's, but we can index up to 3 dimensions. And for example, if you're writing codes that is solving equations on a stencil, it can be convenient to address or to index variables in 2D or 3D. That can come in quite handy. And this also can be translated to kernel abstractions. This index global can be, for example, a Cartesian index that can have several dimensions, not just one. Just a few words about debugging and profiling. If you want to debug GPU codes, the errors can be a bit obscure because it will start complaining also when this code is actually compiled to GPU code. So yes, it will not get the usual nice looking Julia errors. Putting prints in the correct place can be a good way to debug GPU code. CUDA.jl is particularly better equipped for this kind of things because you have macros like qshow, that is the correspondent of the show macro in Julia, that can evaluate an expression directly there in GPU and return the value. qprintline, same thing, and asserts. You can also look at do some introspection. So if you prepend this device code warn type, can give us some type instabilities in the compile code. AMD GPU does not have all this infrastructure as of now. So the easiest is to have prints where we bring back whatever data we have on the CPU, at the moment at least. And yes, there's some documentation for the CUDA.jl package on how we can do this more effectively. But the general idea is, yes, is to have the correct print instruction in the right place. We can do also some profiling to assess the performance of GPU code. We cannot use the regular Julia profilers. So we have to use something that is given by the vendor. For NVIDIA GPUs, we can use the Nsight system. That is basically a framework that can be used to launch profiling runs of a certain program. So we can do nsys launch Julia. And then if we want to profile a particular function, we prepend cuda.addProfile. And this will run and generate a small report that we can inspect with the nsys stats. You can also open it into a graphical user interface for easier inspection. For Julia, there is also a kind of ROC-sys, but it does not really allow you to inspect the results of a profiling in the terminal. One of the ways that is recommended to profile Julia applications is to use ROCprof, especially ROCprof v2, that is available on Lumi. And there is some documentation on the AMD GPU.jl website. The general idea is that we launch ROCprof v2 and we pass it this flag, plugin perfetto, plus what we want to trace. So in this case, we have everything and the executable that we want to profile. So in this case, we have a script and we call it Julia script. And running this will produce a pftrace file. And this can be copied to your local workstation, and then you can upload it onto this web interface that is the Perfetto UI, where you can do open trace file. So you upload basically your trace file onto here, and you get a nice plot where it shows where most of the time in the execution of your code is spent. This can be quite a nice way of profile the bottlenecks in your application. There is also an OmniTrace tool still developed by AMD that can be used especially on high performance computing clusters. And you can read more on the Lumi website about this. One last thing is that a lot of times we would like to write code that is able to decide if we can use a GPU or not. So yes, we would like it to be able to offload onto GPU, otherwise go for a normal CPU execution. The problem is calling CUDA.jl or AMD.jl, AMD GPU.jl functions when a GPU is not present, or where the toolkit is not present, can give a runtime error. So both CUDA and AMD GPU have this functional function that will return true or false, depending if the runtime can access a GPU. So if a GPU is strictly required for the code to run, then we can just put an assert and have CUDA or AMD GPU or whatever vendor.functional, check if it's true, otherwise we exit. But oftentimes we want to be able to use GPU arrays if they're available, otherwise not. And one way of doing it is to check if the GPU backend is functional, and then basically make it so that the arrays become GPU arrays. Otherwise, we keep them on the CPU. The CUDA.gel documentation has a couple of other solutions to this problem. There are some advantages and disadvantages to each of them, because in one case we have to copy things, in other cases we can have type instabilities, but the general idea is to have strategic if-else conditions that lets us check if we have access to GPU or not. And then if you go for the kernel abstractions route, you can have the same code that will be dispatched on whatever backend you find through these if-else conditions. Yes, I think that was it from my perspective. We have a number of exercises porting the functions that we have created in previous episodes, like square root sum, and comparing a broadcast to the kernel we created. The Laplace function can be quite interesting to look at because it's very local and should work quite well on a GPU, and is also featured in an episode later today in the advanced exercises. Yes, so I think it can be time for exercises, and we will be here if you have questions.
Yeah, so in this section we'll look at how to interface to C, Fortran, and Python from Julia. So why would we want to interface to other languages from Julia? So Julia's advantage is its speed, and we've shown in the motivation, for example, that Julia's fast out of the box and without having to do kind of additional steps. And in this regard, it solves the two-language problem. And most libraries can be written in pure Julia, so there's technically no need to write C or Fortran for performance. But because there are already many well-established libraries written in C or Fortran, we would like to take advantage of this without having to re-implement them. And also, if you consider, for example, like Linux, it's written in C, so it is nice to be able to interface to the file system operations and stuff like that. And for this reason, it is, or for this reason, Julia supports kind of ability to natively call C and Fortran functions. And Julia has this no boilerplate philosophy where every functions can be called directly from Julia without any glue code generation or compilation, even from the interactive prompt. So next we'll show a couple examples on how to interface to C code, and Jongle will show how to interface into Fortran code and also how to call Python from Julia. So we can interface to shared C libraries from Julia using the call function. That also works for Fortran shared libraries. These shared libraries, they are usually these files with .so file extension, at least on Linux, that you can find even installed usually for example, if you happen to be on a Linux machine, usually something like user lib. Let's see. Somewhere here should be a bunch of SO files for different programs. Maybe, I don't know. But anyway, they're example of a shared library. And if we want to do it ourselves, we need to invoke compilers like GCC or CLang with the shared flag and the FPIC option. And when we call the shared library with the C call from Julia, it will be as fast as natively call it from C code. So there is no extra overhead at all because Julia compiles the code. Now we look at this example of computing the mean from an array of C-long integers, so those are 64-bit integers, using this code. So I have the file here, it's the exactly same, and we can compile it to the shared object using this GCC command. That should be pretty fast, and it produces the SO file. We can also, for example, use the file command to look at what it produces the ELF shared object file, and it should say that it's dynamically linked. And then we can look at how to use the C call to call that mean function from Julia. So let's start the Julia REPL. Then let's instantiate a couple variables. This will be the input array and the length of the array. These are given as the input to the function. Then you may want to convert these to the sort of C equivalent, although in this case I think the C long is just 64-bit integer, so this conversion is not necessary here, but it could be if we were converting from 32-bit integer to 64-bit integer or vice versa. And then we use the C call. So here, first we supply the name of the function. So that would be the name of the function in the C code. Then we provide the path to the shared object file. It's in the current working directory. So that's why I'm using the dot and the slash here. Then we give the output type C double. I think that's just 64-bit floating point. Then we supply a tuple of the input types. So a pointer to the array and size of the array, and then the actual input arguments. And that should compute the mean of the values, which we provided here. And if you take this one step further, you may want to, if you're calling it often or it's part of your library, you may want to create a wrapper function for that. it would look something like this. So ordering Julia function, taking the arguments, the array and the length of the array, and calling the mean function. But we can sort of do even better to, because Julia arrays natively always store the or have the length of the array, so we can make another method for the mean that just takes in the array that queries the length of the array in Julian and supplies both of those input values to the first method that finally calls the C code. And then we should be able to just do something like this. I guess we could even make this more generic by not providing concrete types here, but arbitrary integers that would be converted into the correct types if we would like to do that. But anyway, here's a very brief example of how to call shared objects from Julia. And now Jonglei will showcase the Fortran example for us.
Yes, let me share the screen. Yes, for Yang talk about the C part, I would like to highlight one thing. Here we provided two functions, wrappers. The first one is you should input array and the length of the array. The second is just the array or the vector. But what's the difference for this one? We know that Python can dispatch the right method for us when we make the call. But you should know that if you provided the wrong argument for this one, you might get an error. Here is the left part. You can see it. This is the Drupal notebook I prepared yesterday. So you can see that we first define the function like this. Then we can make this call, can get the correct result. And if we provide another number, for example, 4, which means that we will get the average value of the first 4 items right here. And it does not count this the 5, 6, and 7 right here. It's okay, because we can get the average value from some part. But if we provide another one, for example, 10, this number is larger than the length of this array, you will get a wrong number. Can this 9.1 something right here? But we know that this is not true. What is the problem and where we get this error? It is related to the memory issues.
Yeah,
Yes.
it does accesses memory outside.
Yeah, accesses the wrong memory, because here we just list the number of 10, which means that we will take 10 numbers from this memory issues. The first where we start from this one, from the memory location for 1 here, means for the first 7 items it is here, but for the 8s, 9s, and 10s we don't know what is that number right there, because it might be wrong number. It might be something stored there, but we did not release the memory. Something we run the code before. That's each time if you run this one, you might get a different result. That is why you should pay more attention about this. Either you provide the correct length of this array, or you don't need. We don't want to just input more items like this. That's why the second wrapper function is provided. We don't provide the length of this array. We just ask the function to calculate the length of this array. Automatically, we can get the average value of the first argument. That is the list, array, or vector, like this. Yes, let's move on to talk about the interfacing of Julia with Fortran. So you know how Julia interface with C, and you will get to know how the procedure should be the same for interfacing Julia with Fortran. But the only thing you need to know is that the name of the function or the name of the subroutine, because in Fortran we call it the subroutine. You should know how to make the call. During the compilation, Fortran compiler usually generates a main name by appending a underscore before the name name of the subroutine, or add two underscores before the name of the Fortran module. I will show this part later. Here we have a code example like this. We define a module called Julia Fortran. We define the four subroutines, that is the four functions in this module. From the name of these subroutines, you can figure out what are these subroutines doing right here. The first is add, which means that add two variables. Quite straightforward. The second is add sub, means the combination of addition and subtraction of two variables. The third one is concatenate. It means the concatenation of two strings. We combine these two strings together and get a new result, get the new output. The fourth one is add array. You can see we have four arguments right here, which means the addition of two arrays, or I can say two vectors, similar to the element-wise operation in Julia. We compile this Fortran code, and we can get the shared object like as Julia Fortran.so. If you use Linux machine, you can run the command like this. If you use Mac, it might be get an error. For example, the library not found for the system. Then you should provide the correct link, correct path for this shared library. How to do? It's the gfortran. The first one is the same, and the -l, and put it to the correct path for the error system right here. Then we can use Julia C call function to call the Fortran subroutines or Fortran functions. Yes, let's see what is the first one. I have prepared the Ruby notebook. This is for the C. For Fortran, it is here. Yes, first is to make the call and to call this add subroutine. You can see what we should provide. This is the name of the add is the name of the subroutine or the function, but before that, we should add the name of the module. There's a double underscore right here before the name of the module, and then underscore mode is short for module, and then another underscore, then the name of the Fortran subroutine. Clear, right? And then the second is very straightforward. That's the name of the shared object. And then the type for the output and the type for the input. These are two float type. We provide the two numbers right here, 1.1 and 3.5. Yeah, we can get the result. You can see this is what I run the code yesterday. And straightforward. The only thing is you need to pay more attention is the name of the function and how to make it critical. Yeah, as I mentioned before, we can write a wrapper thing. We can put this call into a function, and we can just directly use this function to make the call. Yeah, it's quite simple to simplify the column size. Number two is we're going to make this add sub to call this Fortran function, Fortran subroutine. The procedure is the same, but here we at the beginning we need to define two pointers right here, and then make the call. Permutation. This is the name of the Fortran subroutine, and the others is almost the same. But here we need two extra arguments. These are the two pointers we defined at the beginning. Why we need it here? Because we need to return some result. We need to get some result from this call. And once we make this C call, and we use X square bracket and Y square bracket to extract the result from the address the predefined pointers pointing to. We know what's the number right there. Then we extract the result and then return this to result where to where we make the call. And you see, once we make this call, we get a tuple. This the first one is the addition of the two variables. The second is subtraction of these two variables. Number third is you can see it here. We call the concatenate Fortran subroutine. As I mentioned before, this subroutine is used to concatenate two strings. If you can see, concatenate, how to make this call? Concatenate, one is the first string is hello, and the second is Julia. Then we get the result. Hello, Julia. The same. And the name is here, concatenate. The other is the same, the name of the module, and then mode, and then. But here we need extra things about the size of this string for B, string B, and the string A, and the size of the output. Yes. Then we come to the last one about the addition of two arrays. The precise is the same as we just provide the two arrays, or you can call it a list in Python, and then we can get the result in the 4-element vector. This is the similar to the element-wise operation in Julia. But we, as Fortran can do this, then we can just directly make this call. For the Fortran code, we call it the Julia Fortran F90. It is available, and the Jupyter Notebook is available here. If you have installed the Fortran compiler in your computer, you can run this Jupyter Notebook and get the correct results right here. If no, probably you can use Lumi and just copy paste to the script and try to get the result like this. This is the interfacing of Julia with Fortran. Let's continue to talk about the interesting part, that is the interfacing of Julia with Python. Why is it interesting? Because this provides a powerful procedure to leverage the strengths of the two languages. We know that the community of Python is quite strong, and there are lots of libraries developed, there are lots of people using Python to develop their own code. And I should say that the community for Julia is less than that for Python. But if you can the resource, you can use the packages, libraries developed using Python. That's quite straightforward. It saves lots of energy and source to build everything from scratch. That's why we are going to make this call, how to use Julia to call Python. Actually, there are two ways for the interfacing of Julia and Python. That is, you can call Python from Julia, or you can call Julia from Python. As this workshop is mainly focusing on the Julia, so I will talk about calling Python from Julia. I will have a short demo about how to make the call Julia using Python in minutes. For make this call, calling Python from Julia, we need this package called PyCore right here. using the package manager to add this package and then use it to do a simple calculation. You can see it. I have the Jupyter notebook right here. Yes. Let me see. Yes. Using PKG add the PyCore and then doing the simple arithmetic calculation, you can get the result like this. And you can do more. That is, you can define a function like this called we can define it like this called pi string. Yes. If you define the pi strings like this is the same as that you for the interfacing of Julia with C and Fortran. Here it defines two functions like this: sum my argument A and B, and get the nth element from this array, and then return this character. And how to make this call? You can just type pi string and with the name of the string and then argument like this. And if we just pass 1 and 4, we get the result 5. And if you pass two strings like this, you can get a two-element vector that is to perform element-wise operation on these two arguments. This is the first argument, this is the second argument. And we can do more. If the second is just a number, you can also consider this is a string with the two same items like this. This each item in the first vector will add this number and get a new vector. And for the function to get the nth element from this array is the same. You can see if we just type 1, we can get that is the second item from this string, because we have this. If we type 0, we can get this the first one. And if we get type 5, this is the last one. If we type 6, this is out of the range of this list. Then you can get error information like this. So pay more attention to know which what is the last the index for the last element in this input string. It is more. What is more that I mentioned that in Python we have lots of packages and libraries developed using Python, and actually you can directly use these packages. For example, NumPy. How to make this? Just my py import and the name of this library, and then you can make this quite simple to generate the matrix 2 by 3 matrix like this, and then do them arithmetic calculations like this. Yes, somewhat simple, right? I mentioned this. You can make the call from the math library, and you can define your own functions, and or you can use you can make the call from available Python packages. I would like to mention another part, that is calling Julia from Python. So it is right here, but I will switch to this computer. You can see here, right? The left is my terminal, the right is the web browser. Okay. If you call Julia from Python, it is straightforward, and besides you need the PyCore module, you need to install another one called PyJulia. As the command will be like this: Python 3-m pip to install. Here, just the name is not PyJulia, it is Julia. As I have installed this in my computer, so I will skip this step. I will move on. I would like to mention that I have this Python called Julia.gl this document. I will use this one later to make the call. When I type the Python 3, come to the Python programming environment, I have this file in the same directory. And then we come to this Python programming environment, import Julia, and then Julia install. I can install this package. It take for a while, and then you can get the result. See what you can get right here. Info, Julia executable right here, and then try to import PyCore. PyCore is already installed too, and I made the troubles using this. Yeah, it happened, but at least when I make the call, there's no issues, no errors like this. The Julia Python executable is right here, and the Julia is right here. Then we compile the module. Of course, we don't do this. We just come to this Julia script. Here, this is the content for the Python code julia.gl. I just copy paste to prepare this document, and in the same directory when I come to the Python programming environment. How to include this one? The command is this gl.include, as it is here, gl.include, and then the name of this Julia script. And then you can come to this command. There's a warning because there are some changes, and how it's recommended, and the package recommended me to use this one from Julia import main.name. I will mention this later, but I see I got this PyCore Julia wrap get ends element right here. Yes, this is right here. If there's no error, then you can directly get this reminder. Then from PySpark to call this Julia, the subroutine, the function is hello world. This is the first one. Just print hello world at the terminal. You see, we got this. And the second is the summation of two arguments, a plus b. If the two argument is a two list or two strings like this, 1, 2, 3, 4, 5, 6, then we get a new array. This is the element-wise operation on these two arguments. When I make the call to get the element from this string, I get some not error, but I get the result, but some warning from the package. What should I do? Do like this. From Julia, import main dot. Then this is the name of the Julia function, and then this is string. This is the index, which number are you going to get? Instead of using this one, gl.them. Then you can get the results. There's no warning like this. This is the update from this package. And we can do more about by embed the Julia code into the Python code using the evo function. How to do this? Right, command like this. You can just copy and paste this to the Python programming environment, and then they get the results. PyCore grep function product, and then make this call. Oh, give me a sec. I need to move this further. Yes, and then to input the two variables, and then you can get the result. And actually, one thing I should mention that in Julia, you can use dot notations to perform the element-wise operations, but this does not work in Python because Python does not have the syntax like this. If you want to do, you can rely on the Julia's evo function, but put this inside of this core. Then you can get the result. Gets the result from the element-wise operation like this. Yep. There should be more interesting things for the interfacing of Julia with this programming. I mean, not only to Python right here. You call Python from Julia or you call Julia from Python, but the others more, for example, the interfacing of Julia with, for example, right here, with R, with MATLAB, with Java, with a lot of packages like this. So actually, you can see that with these packages, you can call R, call MATLAB, call Java from Julia, or you can call Julia from your R code, from a MATLAB code and the Java code. Well, quite interesting. To I hope that you can try to take time to explore these packages, and it might get something interesting that can be useful for your project. And also some reading materials. And yeah, as I mentioned, this time these materials are is still in the development, and if you can get, and this is quite interesting, and you can probably update the code for your project. Well, to this end, I will say a short summary about this episode. So Julia has significant interfacing with compiled and interpreted language. For compiled, it will be C and Fortran. We did not mention C++, but there are also packages for you to for the interfacing of Julia with C++. And interfacing of okay, talk about the interpreted. It can be Python and MATLAB or there are lots of packages in the development. And the interfacing of Julia with C and Fortran is achieved via the C core syntax. It's almost the same. Just pay more attention to the name of the function or the name of the subroutine. There should be an underscore before the name if you're using the Julia to call the Fortran subroutine. Interfacing of Julia with Python is achieved by the PyCore or PyJulia. So you can, as I mentioned, you can make the core the Python code from Julia. You can make the Julia code from Python, and to see you can see what's the difference, and the efficiency might be varies depending on which mode you're going to use. Yes, I'm thinking I will stop here. Let's take time to play with the code, interfacing of Julia with C, with Fortran, and with Python. Just leave your comment and share the comment, and we play with the code for 20 minutes. Yes, this is the optional part about the advanced accesses. Here is quite simple user case that the heat flow in two-dimensional area. If you remember the when I talk about the writing performant Julia code, we have another example that is we became that to a small project. It's similar to that with but with different initial conditions like this. Here it is quite straightforward. The heat flow means object obtained to local temperature difference, and then we set the system with the initial temperature distribution. We will see how the distribution change as time evolves. The stencil computation, the equation is quite the same as we mentioned before. This is the diffusion equation, but if we put this in the code, it will be like this. This is the 5-point stencil. This is the central cell. The value of the central cell is dependent on the value of the four neighbors for the two-dimensional case. And how to do this? We have the code. It is available right here. And we divided the system into number of cells, and then iteratively to update the distribution of the temperature across all these cells. This is the same as the system I mentioned before. First, you define the physical system, how many cells in X and Y direction, then initialize the system by giving the initial value distribution, initial temperature distribution to all cells within the 2D case, and then evolve run, for example, run the code for 1,000 steps or 10,000 steps. You can visualize the result. How did it change? And then visualize this result. Here is the evolution of the here's the visualization. We run this code for a long time. Every time we give this initial value at the boundary part and the central part, and then we can see how it evolved from here to here, and then this is the last. I can't remember how long we run this code, but it's a long time for this one. Okay, you have the code is here, main.gl, the core part of .gl to see how use this one, and the heat.gl means the heat diffusion. We set the initial value for the physical system and do the evolution, and the feed is the structure thing, and this we also need the benchmark tool package and the progress meter package with the hash key like this, and put this um, for plot. There's no necessary to use this one. I think the latest version is okay. So just copy paste prepare this project Tomo, and use the package manager to add these two packages, and then run the code. Here is the tips how to run the code. Copy the source from the code box above, activate the program environment, and using the project the Tomo file, run the script main.gl, and the option to visualize the result, and then the benchmark, and then study the code and to the porting from the using CPU and GPU, and also use the inbound to see if you can get the benefit. Usually you can get this as I mentioned, as I have demonstrated this using the inbound. You can get benefit like say 50%, and the solution to this optimized benchmark is available over here. So multithreading and using the evolve. If you using multithreading, how about the scaling of this one? And then it will adapt the state problem to the GPU porting. This is the CPU part, and how to port the code from CPU to GPU. And you see inbound for each individual direction. We use the inbound, which means we can save some time and probably even more if for this both X derivative and Y derivative. And you can also try to use the shared array in this student problem to see if you can get things as I demonstrated before. Using the static array, if you have this arrays, you can get some kind of benefit. Solution for this benchmarking and note for the performance to see. The last step is to port the code from CPU to GPU version, and how to write the kernel functions, and how to get the exact result, maybe the mapping from CPU to GPU. You have to use the thread index, block dimension, and the block index, and you should know the mapping from CPU to one by one. As such, you can extract the result from GPU to CPU, and then before the data visualization. Yes, and we provided a hint and also some solution for some accesses and try to make play with the code and make the comparison to see. Hope that you can get, because this is quite interesting project, and if you can run this, I hope you can adapt your code from CPU to GPU, quite straightforward using Julia. Even the code is written in C, Fortran, or in Python.